Welcome to the third talk of this Pages 2K Network seminar series. The Pages 2K Network is one of the longest running working groups at Pages, having been established in 2008 and now in its third phase, which will end at the end of this year. To learn more about the 2K Network and to join our mailing list in case you're not on it already, please visit our webpage that I'm putting in the chat right now. Today's talk will be presented by Michael Sigl. Michael is a specialist in ice core chemistry. He completed his PhD at the University of Bern in 2009, held postdoc positions at the Desert Research Institute, Paul Scherrer Institute, and the University of Oslo before returning to Bern in 2019, where he is now an assistant professor and holds an ERC Consolidator grant, timing of Holocene volcanic eruptions and their radiative aerosol forcing, or TERRA. Michael is one of the leaders of the Pages Working Group on Volcanic Impacts on Climate and Society, and I'll be putting the link to that webpage in the chat as well, in case you're interested in learning more. He's also very well known to many of us as the author of many highly cited articles focusing on volcanic activity and chronologies over the last few thousand years, which will also be the topic of his presentation today. So with that, I turn the floor over to Michael.
Thank you, Sarah, for this kind introduction, and thanks also the organizers of the whole webinar for hosting this series. And as Sarah told already, so Pages 2K Network is one of the longest running networks on the Pages, and the Pages itself is 30 years old now, and exactly the same age is the last major volcanic eruption. So Pinatubo just had its 30th birthday yesterday, and I got in contact with the Pages 2K Network only 10 years ago when I was looking. So I was in a long distance transatlantic relationship, and I was looking for opportunity to exchange ice core analysis in Reno with a trip to Europe, and there came up this opportunity of a workshop related to the Pages 2K Antarctica working group. And in this workshop, we aim to synchronize ice cores from Antarctica using volcanoes as stratigraphic marker events. And basically since then, so since 10 years, the volcanoes were remaining a major topic of my career and my scientific interest. So today I would like to give a little bit of an overview of how we can use ice cores to reconstruct volcanism in the past, and focus specifically on chronologies, and also looking at aspects that are relevant also for the Pages 2K network to look for further improvements of proxy reconstructions for the past. And I'm doing this mostly for the last 2,000 years, and give a brief outlook over some work that I'm currently doing with the TERRA project that is extending this record further back in time. So those of you, here it is, those of you who had the chance to visit Rafi Neukomm's talk will be familiar to this figure. So that comes from the most recent Pages 2K consortium reconstructions, or reconstruction of global scale temperatures, 7 different reconstructions with different methods for the last 1,000 years. And that's the 7 colors, and then you see the range of simulated temperature response from a range of climate models in the framework of the CMIP5 PMIP3 project. You do see that volcanoes are certainly one of the main drivers for multi-decadal, 2-decadal scale variability over the last 1,000 years. You also see certain mismatches. For example, here in this period around 1100, there's certainly a strong cooling in the proxies that the models currently do not take up. And I do hope that with the new CMIP6 model runs that are now produced currently by different labs, that these offsets will become less relevant, because we have an updated volcanic forcing series for this period, which is the series is in green. So that's the recommended volcanic forcing for CMIP6, PMIP4 model simulations. And in my talk, I will basically summarize all 3 of these records. So I will introduce the basic volcanic forcing that was used by climate models until today, so the CMIP5 model family. Then I will introduce how we can improve this volcanic forcing to get to this CMIP6 reconstruction. And then there's also some ice core records in the proxies, and I would also like to highlight how we can improve the proxy response by correcting some of the ice core records to more precise chronologies. So that's the outline of my talk. So starting with the introduction of how we can derive volcanic forcing from ice cores, then focus a little bit on ice core chronologies in general, and then present a few of the chronologies that are currently used by the community. Then I come to the temperature response. So there's a lot of other responses from volcanic eruptions, but the temperature response is the most immediate and direct one, and we have a good understanding from especially tree ring records, also from multiproxy records and from models. And here I will focus on the 2000-year period. So there's much more done on the last 1,000 years, but I would rather shift the focus to have a pages 2K perspective, so the full common era. And then at the very end, one of the outlook is how can we improve the proxy reconstruction for the first millennium. And the second outlook would be how can we extend the volcanic forcing back in time with a first example about the Bronze Age eruptions of Thera and Antarctica. So I'm not going to the very early in the pioneering days when people recognized the potential of ice cores to hold a record of ancient volcanic eruptions. So that was done in the 80s already. And I list a few of the relevant literature from Klaus Hammer, Langway. So French groups, Danish groups, US groups started to explore this novel proxy in the ice cores that you can detect volcanic eruptions by the acids that these volcanic eruptions produce after the emission of strong amounts of sulfuric gases. And this is now already in the main area of ice core research. So the GISP2 record, that's a US program that was taking place at the same time than the European program, the GRIP record. And that was providing for the first time a 2000-year sulfate record for the common era. And this is still today the only record from Greenland that is basically covering the entire last 100,000 years. It's fairly complete over the Holocene and gives a long-term perspective of volcanism between the glacial Holocene and present day. But there are also certain limitations which are marked here in red, for example. Pollution, so you have a lot of anthropogenic pollution starting in the 20th century, which is making comparisons or calibration against observations from satellites and ground-based observations very difficult because you can hardly detect the volcanoes. You also have periods with data gaps. There's a very prominent gap here in the 6th century, which I will later come on, that there are some very interesting eruptions in that period. And of course, these data gaps then have implications for the dating of the volcanoes below this data gap. And here you see one very large sulfate signal is marked, that is 79 AD. And that was basically inherited by a match to another ice core. So the parallel European GRIP core dated this eruption to 79 AD. And that was then used by the GISP community as a age marker to synchronize again the GISP2 record after there was this data gap in the 6th century. And I will come back to the Vesuvius. So the 79 AD is the year of the historic Vesuvius eruption, and I will come back to this issue later on. So, but basically the volcanic history is well recorded in this record, and you can see in this small inset a comparison of the original GISP2 record, which is very coarse resolution, so it's biannual, one value every 2 years. And overlain are two other reconstructions with high resolution, so 1 centimeter resolution. One is from Summit, so exactly the same place, like the GISP core, but drilled in 2015. And the other one is from Northwest Greenland. And this is just to demonstrate you that there's a lot more you can gain in terms of information from present day measurements of sulfur than you could in the past. So you can look at the relative evolution of these signatures. You can derive duration of a volcanic sulfur deposition, which is very informative and tells you a lot about the sources of these events. and the climate impact potential. So then to come back into the climate, to the history of volcanic forcing reconstruction, I think a lot of the work was then taken over from atmospheric scientists, so mostly people with a modeling background, like Tom Crowley, L. Robock, Caspar Ammann. So they were using then the ice core sulfate records that have been published over the last 30 years from Greenland, from Antarctica, and derived estimates of aerosol optical depth or of sulfate burden in the stratosphere, and calibrated that against Pinatubo. And in that way, you could link the observed sulfate concentrations in the ice cores with observed perturbations of the stratosphere, and basically calibrate the ice core concentration measurements to derive volcanic forcing in the past. So that's on the example of the Pinatubo eruption here. And besides the sulfate concentrations, there are also many new proxies that hold information about specific information about past volcanic eruptions. So I'm having this sketch here that Will Hutchinson provided kindly, and that shows us a little bit the approach that we are currently following in this project, how we can derive information about volcanic eruptions using the fingerprint these eruptions leave in the ice sheet. So of course, the sulfate concentrations remain one of the most important points, but we also have indications of the tephra, so presence of small little shards that provide much more detailed information about the specific source of any volcanic event, which you cannot derive from the sulfate alone. Also, sulfur isotopes hold information about if the sulfate aerosol has been formed in this high stratosphere or in the troposphere, and also other proxies like halogen content, trace metal content, holds information about specific source areas and can be used to infer information about the source of volcanic eruptions in the ice core. So that's the multi-parameter fingerprinting tools that we are applying to infer this information from the polar ice cores. And that was basically possible because there was, in the last 10 years, a revolution going on in the ice core science, and that is called continuous flow analysis, or CFA. And that describes basically the principle. I can start the video here, then you can see one example. So you see now 6 meters of ice core being continuously melted. So it's a real-time measurement. And so you slowly melt the ice, and while the ice melts, you pump away the meltwater and directly analyze all the impurities in this ice. And that allows you to have a lot of elements. So you get 30 to 40 different elements, which are all co-registered in depth and age. You get very low detection limits. That is important, for example, to estimate the sulfur concentrations. You get a high depth resolution and therefore time resolution. So that gives very precise and accurate dating then. And the measurement time, as you can see, 6 meters have just been analyzed within 1.5 hours. You can then start to build up arrays of ice cores like El Robock and Chao Chao Gao did. By collecting the ice cores, you can directly now improve this spatial information by adding a lot of more ice cores. Oh, sorry, I was too quick here. I go back. And that's something I think we can nicely see here. So if you start in the upper panel, then you see just the numbers of ice cores that contributed to the Antarctic composite that was used by Chao Chao Gao in their volcanic forcing reconstruction. And you can easily see that they are dropping out very quickly. The further you go back in time, the fewer information you have, and you have only 2 ice cores that are longer than 1,500 years. And then with this CFA analysis, within 6 years, we were really able to fill up a lot of this common era information. So you see in the right upper panel the distribution of the sulfate. So we have now a complete window, a complete map of Antarctic sites that are covered with these ice cores, and therefore we can directly link the sulfate deposition from an event in the 6th century with that of Tambora or Pinatubo, for example, and then calibrate these events. So that is certainly one of the big advantages of this CFA techniques, that you can just build up large arrays and get a lot of spatial information, also stronger robustness in the estimates. And the other great advantage that I want to highlight here is that you can track down specific extreme events. And that is because of the co-registration of all this impurity measurements that you have when you analyze it on a CFA system. Then you have information that allows you to identify the source of these volcanic eruptions, for example. And here's one example that is the Oeschger 2 eruption. We were able to identify that in the ice core and also date it to the winter season between 44 and 43 BC, so before the Common Era. And the reason why we could identify that, that's something you can see here on the right side. So that comes from this CFA analysis of the North Grip ice core. And you see a very large sulfur spike around 43, 42 BC. This is peaking. And right on the shoulder, so on the older shoulder, so prior to the arrival of the major sulfate deposition, you have a very sharp, short-lived deposition event of coarse particles. So that is insoluble particles between 5 to 10 micrometer. And in relation to the sulfur peak, that is a clear-cut indicator for the presence of volcanic ash. So that is cryptotephra that is present just before the stratospheric input from the sulfate aerosol starts. You get the deposition of the ash shards. So we were able to collect from a parallel core then the corresponding ice section, and then we extracted cryptotephra shards and did the geochemistry of these cryptotephra shards and made then the chemical or elemental fingerprint to the Oeschger caldera. And that feeds them back again. So if you know the Oeschger caldera is the source, then we can also constrain the timing of the event, because the aerosol transport for a high latitude eruption between Alaska to Greenland, it's a couple of days. So that means that the exact timing of this particle spike is then the eruption date. And that allows us then to pinpoint it to winter. And that's important information. If you then try to simulate this event, then you have the magnitude from the sulfur concentrations, the location from the tephra fingerprint, and then the seasonal information from this particle spike here in 44, 43. And then you get a more realistic simulation of the climate impacts, which we can see then in the panel B below, that you get a very strong northern hemispheric cooling over North America, Europe, and Asia. So that was just to demonstrate the subseasonal dating and the importance of having this co-registered measurements. But coming now back more broadly to ice core dating. So ice core dating is done for many years, and they're all similar in a way that you are measuring many impurities or stable isotopes of the water in the ice, and many of them have a seasonal cycle, either cold summers and warm cold summers and cold winters and warm summers, so in the stable isotopes, or specific impurities. And in that case, I show an example from Antarctica, where black carbon has a very strong seasonal cycle. So these are black carbon concentrations around 6,000 pp. And you have a strong burning cycle every year in the southern hemisphere, driven by changes of the ITCZ. And that is then producing biomass burning plumes that reach Antarctica, and then you can basically count these black carbon cycles. But if you're counting over thousands and tens of thousands of years, like here, you're already 6,000 years long, there are some ambiguous years where you're not certain, where the interpretation might differ between different groups, and therefore you get uncertainty in ice core dating if you count annual layers. And because of these ice core uncertainties, people have always sought to use reference horizons, so some fixed age markers that are ideally unique and well linked to the event that they should represent, and have an absolute independent dated calendar age, for example. And for the GICCO5, so now that's ice core dating scheme for Greenland. The one before I showed was for Antarctica. And for the Greenland dating framework, They listed, for example, in the common era, there were 5 major reference horizons. So you identify these reference horizons in all the ice cores. So they are all relatively dated and securely dated. So they are, you can connect the ice core records relative to each other. But some of them also have given here a maximum counting error of 0. So they are assumed to represent historic events, and therefore they have no dating uncertainties. And in this case, these are 3 eruptions. And 2 of these I marked here yellow. And I think there's strong evidence that these 2 yellow events are actually not attributed to the correct historic event, and that those are wrong. And one of them is the Vesuvio eruption. So you see it in the lower panel, the NEAM S1 record in 410.6 meter has this acidity layer that you can measure in the field already. So that was attributed to Vesuvio, so Vesuvius in Italy, and therefore had a maximum counting error of 0 here because it was assumed to be a historical event. And we tested this assumption if it's really from Vesuvius by sampling the same event, so the NEAM S1 core. We collected tephra samples around this sulfur peak, and we actually did find tephra samples as shards and measured the geochemistry of these shards in the direct vicinity of the sulfur peak, but they have an andesitic composition, so certainly an elemental composition that is distinct from Vesuvius, so from the historic eruption of Vesuvius, and it's also distinct from the grip tephra, so the European record that has been linked to the Vesuvius eruption before, and we can currently not attribute it to a specific event, but the geochemistry would match a few candidates in the Pacific region. And just today, the paper that Jill Blunkett put together is appeared on Climate of the Past discussion, so you can read in more detail about this Vesuvius dating story. Luckily for us, we had another reference horizon just coming up, and that's thanks to the work from Fusa Miyake from Japan. So she measured in high resolution C14 content in tree rings, and she found this rapid enrichment of the C14 content between 774 and 775 CE in 2 trees, which subsequently has been confirmed to be existing in all tree rings, so southern hemisphere, northern hemisphere, throughout the last, over the globe. And that is thought to derive from an extraterrestrial radiation event. And we therefore assume that we would see a similar increase in the 10 beryllium that would also form by solar, by extraterrestrial radiation. And therefore we measured the NEAM S1 core in very high annual resolution for 10 beryllium, and we could actually identify this same event in the ice core, and could therefore confirm that there was actually a dating bias in some of these ice core records in the first millennium of about 7 years. So the ice cores were dated 7 years too old previously, and then if we constrain the ice core dating with this event to 775 CE, then we can come up with a new chronology, which we called NS1 2011. And this is now the final product, more or less, if you combine now the Weiss divide, so not the Weiss, the Antarctic ice core records and the Greenland records on the revised and constrained chronology, then you can get an estimate of the stratospheric sulfur injection of these individual eruptions over the last 2,500 years, and also an estimate about their location, based on the assumption that bipolar events, so if you have sulfur deposition in Greenland and Antarctica at the same time, then we attribute a tropical source, so something around 0 if you not have the tephra. If you have only sulfur deposition in Greenland, then we attribute a mid-latitude northern hemisphere source, and if you have only sulfur deposition in Antarctica, we attributed a southern hemisphere mid-latitude source. And that's then the spatial temporal variability of SO2 injection to the stratosphere over the last 2,500 years. And this can basically then be used by climate models that are aiming to simulate the impact of volcanic eruptions on the climate of the last 2,500 years. You can also see that certain periods were more quiet, like the Roman quiet period, medieval quiet period, so with the absence of large volcanic eruptions, and some periods where you had more frequent volcanic eruptions. So that's basically the major reconstruction of volcanic sulfate injection over the last 2,500 years. And with that, I come to the next point, which is then the climate response. And so this is now from the paper in 2015. When we first discovered this dating bias in the ice cores, we wanted to prove that under the revised new dating, the response you see in the Northern Hemisphere tree ring records, which are very climate sensitive to volcanic forcing, is somehow consistent between the early part of the reconstruction and the late part of the reconstruction. So that's why we use this N-tree composite. So it's a composite of 5 tree ring sensitive proxies from North America, Europe, and Eurasia. And these are now plotted on the same axis and the estimated volcanic aerosol forcing from these eruptions. And you can directly see that the clustering of very cold single years or very cold decades with very strong eruptions is very clear and obvious. And the basic question we wanted to answer with that is if it's consistent for the early part and the late part, and that is then answered with this plot here. So this is a superposed epoch analysis. So that's basically putting the segments of the response in the tree rings relative to the eruption dates for the early part of the reconstruction, 500 to 1250 CE, and for the later part. And in both cases, the response looks the same. So you get a very strong climate response, and it's consistent between the early and the late part of the common era. So therefore, we are very confident that ice core reconstructions of volcanic forcing is also very accurate in terms of the timing and precise for the early parts of the first millennium and the years before the common era. Subsequently, in 2016, Ulf Bündgen published this reconstruction that is based on 2 of these tree ring records, so one from the Alps and one from Altai in Siberia, and they discovered that there's a strong multi-decadal to almost centennial scale cooling response in these 2 sites, which they termed then the late antique little ice age, so a kind of a very cold period in the first millennium. And that is now based on 2 ice cores. And already in these 2 ice cores, the year 536 was standing out as the coldest year of the common era. And this is just basically an update, more sophisticated reconstruction using very different methods for calibrating and to constrain the overall uncertainty of these tree ring records, and also expanding the database to 9 regional reconstructions. So this is now basically throughout the Northern Hemisphere, not only Altai and the Alps. And it does actually show that 536 remains one of the coldest year in this period. 536 to 550 is certainly one of the coldest episodes of the common era. It also shows this is based basically on ring width data only, at least the majority of these records. And of course, maximum lateral density has been recognized by the tree ring community as being the better parameter to describe the temperature effect of volcanic eruptions. And that's something that I think Rob Bilson was already mentioning at the last talk. There is certainly potential to expand a lot of these black curves further back in time and get a better understanding of the climate history for the first millennium, also by maximum lateral density records. This is also in stark contrast with the Pages 2K reconstruction that Rafi Neukomm presented. So here, and also 3 weeks ago, when he gave his talk, he was making a case that the 1840s were actually the coldest period of the common era, ranking this 530s period. And that is, of course, a very different database. So the other one was tree rings only. This is now multiproxy reconstructions. And he concluded that there's no evidence for globally coherent warm and cold periods over the pre-industrial common era. And if you look at this pages to K record at the specific year 536, then the reconstructed cooling of 536 would only be 0.25 degrees Celsius based on this global scale reconstruction from the multiproxy record. And that is quite small, especially if you consider the Pinatubo, an eruption that is a fraction of the size of 536, produced observed anomaly of up to 0.5 degrees over the northern hemisphere. So there's certainly a strong dilution of this signal in the pages to K reconstruction, and we can also now use the climate models. So now the CMIP6 model runs, the first ones have been conducted over the last 2,000 years. That's work by Johan Jungklaus and Evelyn van Dijk. So there's 2 runs that are covering the last 2,000 years with the Max Planck Institute system model. And then there's a subset of 10 simulations for this late Antique Little Ice Age period. And you can see that there's a quite strong cooling response in this new simulation that is larger than the one in the 1850s for sure. It's driven by this cluster of 4 large volcanic eruptions. And the overall temperature amplitude is in the range of up to 2 degrees Celsius for the northern hemisphere, following the second eruption in 540 and 1.5 degrees for the 536 event. And that is currently also in the discussion of the pages VIX special issue. So if you want to read up on this study, it's under discussion right now. So Evelyn also made a comparison. So we remember the Altai and the Alps record had this long-lasting climate response that was then called the late Antique Little Ice Age. And you can from the new model simulations also extract the temperature anomalies at the grid sizes, positions of these reconstructions from the Altai and Alps, and that's shown in this plot here. And overall, I think it's quite clear that the persistency that is indicated, for example, in the Altai, it's very, very strong, lasting for many decades. That is certainly not reproduced by the model simulations, although they are lasting the temperature response for 10 to 20 years. It's certainly not a centennial scale cooling anomaly. And the magnitude, of course, that's model dependent, is currently a little bit stronger in the models as compared to the tree ring reconstruction. And I think this is the main findings, that the magnitude for these model simulations are certainly an order of magnitude larger almost than the one you can get from the pages to K 2019 multiproxy record. And why is that? I think I skipped that. Or no, do we have time? Yes, we do. So that's a comparison now of similar to what I did before on the entry record. So a split period approach where we looked at the response of the new tree ring reconstructions from Bündgen for the early period, so 100 to 1200 CE, and here 1200 to 1900 CE. And that is internally consistent, so it's around 0.4 degrees cooling on average following this large volcanic eruptions in this time windows. And it's significantly larger than what you get from the pages 19 database, so an order of 3.5 to 5 times larger. And what is also striking is that the pages to K19, the response is also much more reduced in the first millennium than it is in the second one. So this one is 30% smaller than the response in the later period. And this is striking, but it's actually not very surprising if you look into the proxies that are in the multiproxy compilation. That's not only tree rings, so it's a lot of proxies like ice cores, it's marine sediments, lake sediments, and of course they do not have the annual dating precision that the tree rings have. So on the left side you see tree rings have a very sharp response, but there are very few records, and the multiproxy records are much more abundant, but of course they do not have the resolution and also the dating precision and accuracy to capture all these short-lived events. And in the 2015 paper, I was in the conclusion actually mentioning that our new ice core reconstruction has also implications for the Pages 2K network, and not only the volcanic forcing, but also because ice cores are also included in the proxy network. So if we correct the forcing by 7 years, then we need to apply the same forcing basically to the proxies from the same ice cores, because otherwise, of course, we are inconsistent, and that's why we do not capture the full amplitude and variability if we are not aligning all these proxy records on the exact same time scale. And just here as a comparison, so what is actually in the database in the Pages 2K network? So this is now from the 2017 data that is providing all this metadata, which proxies have been included in this database. And you see that in the late antique Little Ice Age period, you have basically 4 main sources of information, and a quarter is tree rings, and a quarter is ice cores. And we know that the ice cores at that time, they were still on the original dating, which has a dating bias of 7 years. So they're certainly not synchronized with the trees. And if you go back to the Little Ice Age, where Raffi Neukomm saw the strongest cooling response, the picture is completely different. So everything is overwhelmed by tree rings. You have a huge abundance of tree ring records, and the others, ice cores, lake sediments, marine records, only contribute very little. So for these reasons, you would always expect to have a very strong response, climate response in the Little Ice Age compared to the late antique Little Ice Age, just on the basis of the proxy composition in this network. And I can demonstrate it on one example here. So this is taken from the Pages 2013 reconstruction, because it gives you a little bit of an overview which region is taking which proxies. So you see that mid-latitudes are all dominated by tree rings. Antarctica is exclusively ice cores, and then in the Arctic, for example, you have a mixture of lakes, tree rings, and ice cores. And with the current dating, where the ice cores are basically synchronized to the GICC05 chronology, anchored at the Vesuvius eruption, that's the stable isotope record for this time period between 530 to 560. So you see that the cooling and the warming are not always aligned, and they're somehow compensating itself. So you see cooling in Greenland when you have warming in Eurasia, and the other way around, you have warm conditions in Greenland and cold conditions in Eurasia. And you can imagine if you put that in a composite and average, then you're producing a very low frequent signal, and you reduce the amplitude. Just looking at tree rings and ice cores, and then you can also add lake sediments and marine records, which also have not this kind of very high dating precision, then you're of course smoothing out even more variability. If you move, for example, the stable isotope records from Greenland to the NS1 2011 chronology, so to the one that is constrained at 775, then suddenly everything falls into place. So you get the warming conditions, for example, in 530 that you see in Eurasia, they are also seen in Greenland. You get a very strong cooling in Greenland in 537, and that is also lasting for 3 to 4 years. And then you have warm conditions again in 560. So I think just by recalculating the stable isotope records to the most up-to-date chronologies, you can already recover much more of the high frequency variability in this network of proxy reconstructions as compared to before, where the ice cores were consistently biased to old ages. And I think since I'm running out of time, I will probably, or now I can add that one. So now I'm extending the volcanic forcing back in time. And I think the most interesting first period when you extend it from 500 BCE comes when you go into the Bronze Age. So the well-known Santorini Thera eruption, of course, is a major target for any reconstruction of volcanic forcing. And all this uncertainty and controversy regarding the eruption date. So there's a very large range of dates that have been suggested for this eruption, and currently it's believed to be somewhere between the 17th and 16th century BCE. And the Santorini eruption tephra has, for example, never been found in ice cores from Greenland. So that's certainly one of the factors that is also contributing to this large uncertainty. And we are hoping with our new approaches of combining different ice cores, new chronologies, and also new tools like cryptotephra research, sulfur isotopes, to get some new insights into the volcanic forcing of this period. And you see here some 6 ice cores that we collected for this period, some from Antarctica, some from Greenland, and we have aligned them on a common time scale. And now we looked at tephra and identified tephra that is consistent with Anyak Chak, for example. And then we can combine this information like I did before for the 2,500 years and derive estimates of volcanic sulfur injection. And that will then help to constrain, for example, the climate impact of eruptions like this Anyak Chak. And that is emerging then as the largest eruption basically of the last 4,000 years. It's even outranking Okmok, so the largest eruption of the last 4,000 years north of the equator. So it's comparable to Samalas, for example, from Indonesia. And that's what we are currently working. So we are focusing on this time window, but we also hope to expand this reconstruction for the full Holocene. And I guess there would also be then good opportunities to compare with the pages Holocene reconstruction that is also ongoing work. I think from Derek Kaufman is working a lot in that direction. So I wanted to mention it, and it's an ongoing process, so it's nothing is set into stone, but that's coming along very soon. And with that, my take-home message is just the one sentence I said before. So the multi-proxy reconstruction of temperature that include ice cores, that is the pages 2K, but also pages ISO2K and data assimilation products. They have diminished high to mid-latitude frequency and must therefore be updated to accurately capture the timing and full amplitude of paleoclimate variability. So it's not easy, but I think we have now identified these offsets in the ice core records, and it can be fixed. So I think we should update when we have this information, the first millennium record, especially. The second millennium is not affected. So it's basically the first millennium and then also the Holocene that would really benefit from a revision of the ice core records, and the ice core records are also in other data compilations, and therefore I think it's certainly something that we can put on the pages 2K network agenda for the upcoming years. And with that, I would like to thank everybody who contributed, the team here in Bern, the Pages Wix community, the ice core community, and the ERC for the generous funding. And you for your attention.
Thank you so much, Michael. That was a wonderful talk. And we already have a couple of questions. For if anyone else has any questions, feel free to use the chat or raise your hand or open your mic. There's one question from Dallas Abbott, who this came about halfway through the talk, but I don't know the exact slide number. But Dallas asks, are all of the models of cooling show the largest cooling in the most recent eruptions? Can you comment on why that might be?
I don't know exactly. Maybe it was the first one from Raffi Neukomm, this one here?
I think it was not. I don't know if Dallas, if you want to
It was, no, it wasn't. I think he kind of answered the question later on in the talk by saying that they have to update the estimates from the ice core records, but I wondered if a higher temporal sampling in the ice core records would help you.
Yes, no, I think the stable isotope records are fairly highly sampled there. Then just, I think the annual resolution is still, of course, you have diffusion and everything, so you cannot do anything with the sampling itself. But I think the resolution is not the big thing, it's more the dating itself. So if you shift, of course, everything to 7 years younger, then of course the amplitude will be stronger. But that's exactly right. So you would never, with the mix of proxies that we have currently, of course, it's difficult to get anything as cold as Tambora in the, let's say, 200 AD, simply because the proxies do not have the resolution and the dating accuracy. That doesn't mean that if you had a very large eruption in 200 AD, it could have been also much colder than it's currently indicated. I think that's just the limit, and it's very difficult to have a data set that is inclusive and tries to cover the whole globe, and at the same time tries to be as restrictive on dating accuracy and in precision of the measurement. So I think it's a compromise. So you can certainly not recover the full amplitude with a multi-proxy approach, but you can at least, if you have some information that there's dating biases, and you can correct those, and then you can recover more of the information.
Thanks, Michael. And Mike Evans, would you like to open up your mic to ask a question or comment?
Thank you for this talk. This was so much fun and great update. So you answered a question that that I had, like in general for these seminars, which is what should the 2K community be doing next? And it's pretty obvious, updating the databases for chronological improvements for anything related to ice cores. So my question, I guess, is this something that VIX and 2K groups should be taking on? And is there a way to do it in a way such that future improvements, which are probably coming, will be easier to incorporate? Because doing this by hand, would be laborious and subject to mistakes by the community. Thanks.
Yeah, that's certainly something that we should have put on the pages, maybe 2K or pages Holocene agenda. We could also put it on the VIX agenda, so it's somehow overlapping, of course, the interest. So, of course, VIX is also interested in temperature comparison with model. So it's certainly something that we can put on the agenda. And of course, the work that has been done, it's nice that all the stable isotope data, for example, is all already archived. So it should be relatively straightforward to apply then age transfer functions to existing stable isotope databases. And you shouldn't be able to start from scratch if everything is archived in a consistent way. I hope that people who are more familiar, I hope that Nick McKay, people would with more experience in this management of large databases would be able to support at least the community who knows the age, the new updates in the age, in having something working together on a revised version. So it's certainly the ball shouldn't be entirely with the people who are working with the database, also more in the ice core community that has the first-hand knowledge, but you need a little bit, I think, both groups.
A quick question. You showed a slide which was beautiful. It showed the eruptions as a function of amplitude and latitude and time. What publication was that from? That's the one.
Did I get rid of it again? Okay, let's keep it like, sorry.
You had it for a minute and then you went past it.
No, so the measurement, so that's from Matt Toohey and me, 2017 Earth System Science data, the raw data, and we are hoping that we might use this figure maybe in the VIX special issue introduction chapter or something. So it's published data, it's just put together because it's a little bit yeah, better to show it than showing a time series or something like that.
I see published figure, unpublished figure, published data. Got it.
Basically, and a few updates based on new tephra findings, and then the satellite data added from Simon Kahn from 1979. So it's a little bit, a few updates based on the 2017 Earth System Science Data paper.
There's one more question in the chat from Tom DeMille, who's working on high elevation bristlecone pine and asking about ideas about prioritizing. I don't know, Tom, if you want to open your mic to ask, or.
Okay. Hello, can everybody hear me?
Yep.
Yeah, so I just started really, so it's a lot of work because they are very small rings, and that's why nobody actually did MXD before on that. So this the past few months I'm still working on the X-ray physics part of it. So I just wonder, given this location, what years would you propose to prioritize to have a closer look at? So we're looking at 4.2K events, for instance, but I'm rather new in the field as an X-ray CT, so that's why I wanted to have some ideas. Yeah.
So you have it at your hand. How many years? 5,000 years or even more?
6,000 years. So the high elevation, so the oldest, the low elevation are more precipitation sensitive, but the high elevation is temperature sensitive. Yeah. So 6,000.
Yeah, there are certainly many events. So obviously the frost rings as a first guidance. So frost rings are a very strong indicator of volcanic eruptions, but very difficult then to calibrate in terms of the temperature. So if you focus on the frost ring dates, that's certainly a first point. And then there are certainly a few interesting events. So it depends on exactly what your tree ring database is, if it's continuous or, but we can discuss that. So I can give you a few promising dates, I guess.
Yes. Okay. Yeah, I know. So the main advantage with MXD is that it's more quantitative. With the frost rings, it's something that is just visual. So yeah, indeed. Yeah, I'll be happy to discuss later. Yeah. Thank you.
There's a comment also from Jihong Zhou about documentary records. It says that documentary records are missing in Asia, but there are actually a lot of historical records in China. And Michael, I know that I think there are people in the VIX working group who are working on this from a more human perspective, or looking on the impacts on societies. Can you comment on the documentary evidence that is integrated into the data that you've shown here?
Yeah, I've not talked about documentary data, so that's true. There are certain areas like China and also Europe, I guess, where there's a very rich record of documentary record, and they are also employing now methods that you can get quantitative calibration estimates, and they would of course open the door to seasons that are not easily available, for example, to spring, fall, or winter season that is not very easily accessible with tree ring data only. And that's certainly something that is coming up more and more. I think the page has made a own working group now, CRIAS, focusing on documentary data, and we are very happy to employ documentary data, have a lot of strength. So the exact date often, although it depends of course on how it's written down and recorded, and a lot of extra complementary information. Also then later on, if you are interested not only in the direct temperature response, but also some societal responses, and of course documentary data are a very rich source of information. So it's certainly something that we are trying to incorporate as much as possible in the VIX group. But for this talk here, I was focusing only on very simple things like forcing and temperature, not on the more complicated stuff, bringing in the human dimension.
That's understandable. In a limited amount of time, there's only so much you can present. But thank you so much. Are there any last questions? It looks like that's not the case. Nope. Yes, we have one from Yuko.
Can you hear me?
Yes,
Yep.
Yuko, I hear you.
Oh, Yes, thank you very much, Michael, for your comprehensive presentation. I have one question to you about the difficulty of determination of chronology for ice cores which have a very few precipitation rate, like Dome Fuji or maybe Dome Shi ice cores. For example, our Japanese ice cores, Dome Fuji ice cores, have a lack of annual layers, maybe probably say more than 11%. So it is difficult for us to determine the very exact annually recognized yearly scale determination for ice cores, and which is very different from other Arctic and other Antarctic ice cores. I would like to have your opinion for this.
Yeah, I think that's a common problem that we know in the ice core community, that you cannot have both. You cannot have super long records reaching 860,000 years and at the same time have high accumulation and high resolution and high dating precision. So there's a compromise, and the East Antarctica offers mostly long records and also a very strong input from the stratosphere. So that's one of the advantages. So you're basically sampling pure stratosphere in these regions. But then, of course, you have some negative effects, which is then, of course, a very small annual layers or also wind erosion that then might modify specific events, either increasing it or enhancing it. So that's just, I think, the compromise you need to do. So you cannot have, I think, everything high resolution and 860,000 years. And you need to take the good things, so get the sulfate information and the spatial information from East Antarctica, and maybe focus with the dating then on West Antarctica, where you have high precision but not the length. So that's and I think we are doing quite good. So we are covering quite a range of different research questions with very long records and then very precise and short ones. Did it answer your question?
Yeah, I would like to discuss you further for a specific ice cores dating. Yeah, thank you.
Let's do that. I know I owe you an answer, I think.
Thank you. Thank you for your presentations and answers.
Thank you.
Alejandro, would you like to open your mic?
Yes, thank you. Hi, Michael.
Hello.
I have a couple of questions on the figure they're showing right now.
On what?
Sorry, can you hear me?
Yeah, I didn't understand the word, the last one.
Okay, so I have two questions regarding the figure that you're showing right now.
Okay.
One is that on average, the eruptions from the tropics seems to be higher in sulfur content. Is there an explanation for that?
Yes and no. So certainly this period itself was very rich in very strong tropical eruptions and relatively poor in strong high latitude eruptions. So if you go into the Holocene, for example, that might already look different because you had more large eruptions in the mid latitudes. So a little bit is just a coincidence that you just had a lot of tropical large eruptions. And then, of course, it's the way these are calibrated. You are applying different calibration functions. And since the tropical eruptions are defined by having bipolar signals, so Greenland and Antarctica, they will probably be larger because you're adding two different components. But and also I think the lifetime, the sulfur lifetime is also longer for the tropical events. So therefore you have more time to integrate the sulfur over these events than you have for these eruptions here. But the radiative forcing, for example, the annual forcing could be much larger. For example, in 536, the annual forcing in the northern hemisphere is much stronger than the one from 540 because it's accumulating a strong sulfate burden in a short time window. So you get a much stronger opacity of the stratosphere for a nominally smaller injection.
Okay. So, and the next one is that, is the magnitude of the spike related to the size of the eruption in these cases, or how did you estimate the sulfur content? Is from a petrological point of view, or?
Yeah, basically it's the integral, so the overall sulfate over the length of the deposition integrated over 2 to 3 years, depending on the event. That scales not linearly, but to some extent with the injection, also then with the climate impact. So you can say that the larger the sulfate, you cannot say for the ice core, but for the sulfur injection, you can say that the larger the sulfur injection, the bigger the climate impact would be.
Mm-hmm.
But of course, if you have a Greenland ice core, then you can also get very large sulfate spikes from very proximal eruption that you would need to treat those differently. But overall, okay. I think the sulfate strength, so the emission strength is the most important driver of the climate impact. And then, of course, you have, in addition to that, the bloom height, the season, and other parameters.
Okay. Thanks, Michael.
You're welcome.
Thank you so much. I think we should probably wrap this up here. Thank you all for joining us. And thank you, Michael, again, for this wonderful presentation. The 2K Network seminar series will continue after a month break on the 22nd of July with a talk by Georgie Falster about the ISO2K project entitled Using the Stable Isotope Composition of Water to Gain New Insights into Global Hydroclimate Variability Through the Common Era. So we hope you'll join us. I'll also make a plug for a talk on the 7th of September because Michael mentioned Johan Jongklaus and Evelyn van Dijk when he was presenting some CMIP6 results, and that will be, they will be giving a talk on that topic. If you are interested in joining us for any of the future seminars, I'm putting a link into the chat now where you can see the talks that we have planned, and we'll be adding to that as more people sign on. So thank you again, and we look forward to seeing you all in July.